Hello students, welcome to my channel Engineers Academy. Do hit the subscribe button if you haven't done it yet. Now we are going to solve this problem which says that determine the force in each member of the truss in terms of load P and state if the members are in tension or compression. So we are given this truss and we have to find the forces in each and every member in terms of this external load P which is acting vertically downward. So first of all, we will consider the whole truss and we will find the support reaction. So at E, let's say that we have EX reaction, which is going towards the right, let's say, and let's say we have EY reaction. And similarly, at A, we have the roller support. So at A, we will have only one reaction and that must be acting towards the right. So this is, let's say, AX. Now, considering the whole truss, if I apply the summation of moment about point E equals to 0, that will be equal to 0. So the summation of moment about point E equals to 0. The counterclockwise moment is considered to be positive. Now, if we look into this AX, it's going to produce the counterclockwise moment about point E. So I will write AX, and the perpendicular distance or the moment arm of this AX from that point E is this distance from here to here. This distance is the moment arm of AX, and this distance from point E to this particular point is D plus D divided by 2. So D plus D divided by 2 is D plus D divided by 2. This is 3D divided by 2 actually. And this P force is producing the clockwise moment about point E. So this is producing the clockwise moment. So we will write minus. So minus P, and the moment arm of this P, or the perpendicular distance of this external force P from that point E, is this distance, which is this D. So we will multiply this with D, and this is equal to 0. So now we can say that AX multiply by 3D divided by 2 minus PD, this is equal to 0. And if we divide this whole equation by D, so D will cancel out and we will be left with 3 divided by 2AX minus P equals to 0. And from this we can say that AX is equal to 2 divided by 3P. Now X is, in terms of P, is 2 divided by 3P. So let me write here that AX is 2 divided by 3P. So now if I apply the summation of forces along X, that will be equals to 0. So the summation of forces along X while considering the whole truss. So now as we can see that towards the right is our positive X. So now we can see that EX is acting towards the right, that is the positive direction. So I will write plus EX, and AX is also acting towards the right, that is towards the positive X. So plus AX, and AX magnitude is now known, which is 2 divided by 3P. This is equal to 0. So EX is equal to minus 2 divided by 3P. And we can say that EX magnitude is 2 divided by 3P, and it is actually acting towards the left. So this means that the assumed direction of EX is not right. EX is actually acting towards the left. So let me draw that EX towards the left. So this is that EX, and EX magnitude is now, when it is acting towards the left, its magnitude is 2 divided by 3P. And similarly, if I apply the summation of forces along Y, that must be equals to 0 up in the upward direction is our positive Y direction. So now we can say that EY is acting in the positive Y, so plus EY minus the external force in the downward direction, so minus P equals to 0, and EY is equal to P. So this is EY equals to P. EY is acting in the positive Y direction. This is EX. Now let me write that EY is equal to P. Now let's start with joint E. Let me write that joint E. We will solve this problem by using the method of joints. So we will consider a joint E first, and let's cut this member and let's cut this member, and let's assume that ED member is in tension. Let's say that this ED member is in tension. If it is in tension, the force applied by this member on this pin at E will be acting away. So this is FED, and let's say that the member CE is also in tension. So this is FCE. So now, while considering joint E, and if we want to apply the summation of forces along X and Y, we need to resolve this force into its component, that is FCE. So we need to know this angle. We need to know this angle. Let's say that this angle is some angle theta. So we can find this angle theta if we consider this right angle triangle. Now we know this length. This length is D plus D divided by 2, and we know this length, which is D. So we are given this triangle. We are given these dimensions like this. This is D, and D plus D divided by 2 is 3D divided by 2. And this is that angle theta. So now if we apply tan theta to this triangle, so tan theta is equal to perpendicular. Now this is the perpendicular for this angle, and this is the base. So 3D divided by 2 divided by D. So D will cancel out, and we will get tan theta equals to 3 divided by 2. And theta is equal to tan inverse 3 divided by 2. So tan inverse 3 divided by 2, this gives us 56.309, which is, let me write that theta is 56.309. So now we can resolve this FCE into its component. So it will have one component in this direction, and it will have one component in this direction. This one will be the cos component, this one will be FCE cos of theta, and this one will be FCE sine of theta. So now if I apply the summation of forces along X, that must be equals to 0. Towards the right is our positive X direction. So now as we can see that this FCE cos of theta, this is acting towards the right. So we will write plus FCE, and cos of theta, and theta is this 56.309. And similarly we have this EX, which is acting towards the negative direction. So we will write minus EX, and minus EX value is 2 divided by 3p. This is equal to 0. So now FCE is equal to 2 divided by 3p. Let me write it like this: FCE cos of 56.309 is equal to 2 divided by 3p. And if we divide both sides of equation by cos of 56.309, we will get so FCE is equal to 2 divided by 3 times cos of 56.309. This gives me 1.201. Let's say 1.202p. And as we have assumed that the FCE is in tension, and we got the positive sign here, so this means that the assumed direction is accurate and FCE is in tension. So FCE in terms of P is 1.202p, and it is in tension. Now if we apply the summation of forces along Y equals to 0 while considering that joint E, So this is our positive y direction. So now as we can see that we have this FED in the downward direction, that is in the negative direction, so minus FED. And then we have EY, this EY in the positive y direction, so I will write plus P. And then we have this component, this FCE sine of theta. So minus FCE sine of theta, and theta is 56.309, and this is equal to 0. Now we can write that minus FED, and this is FED plus P, and now FCE is known, which is 1.202p sine of 56.309 equals to 0. And now we can write that if I bring this FED to the other side of equation, so we will have FED equals to P minus 1.202p sine of 56.309, and we can take this P is common from both these terms, so we will have 1 minus this into P. So now 1 minus 1.202 sine of 56.309. So we got this as minus 0.00, so which is approximately equals to 0. So FED is approximately equals to 0. So this means that ED member is the zero force member. The ED member is carrying zero load. So FED is equal to 0. So now we know FCE. FCE is 1.202p and FED is 0. Now next we will consider joint A. So let's assume that at joint A, the member AD is in compression. Let's say that the FED and the FAD is acting towards that joint A, and let's say that AB member is in tension. So you write that FAB. So we need to resolve this FAD and FAB into its components, and let me cut these members. So now we need to have these angles. We need to have the angle of FAD with the horizontal and the angle of FAB with the horizontal. So now if I extend this line, so we can see that this length is D divided by 2 and this length is D. So again we can consider this right angle triangle for finding this angle, and similarly we will have that same triangle here as well. So this means that this angle and this angle, both the angles are equal. So now we can use this triangle. This is our theta, and if we apply tan theta, so this is perpendicular and this is the base. So the perpendicular is D divided by 2 and the base is D. So now let's say that this angle is, let's say, alpha. So we can say that tan alpha is perpendicular. So now the perpendicular is this D divided by 2 divided by the base. The base of this triangle is this, which is D divided by D. This will cancel out. We will have tan alpha equals to 1 divided by 2. And we can say that alpha is tan inverse 1 divided by 2. So tan inverse 0.5. This gives me 26.565. So alpha is 26.565 degrees. So now we know angle alpha. On both sides we have angle alpha. So now we can resolve FAD and FAB into its components. So FAD will have one component in this direction. This one will be the cos component, and it will have one component in this direction. And similarly FAB will have one component in this direction like this, and it will have one component in the downward direction like this. So this one will be FAB cos of alpha, and this one will be FAB sine of alpha, and similarly this one will be FAD cos of alpha, and this one will be FAD sine of alpha. Now considering joint A, if I apply the summation of forces along y, so the summation of forces along y will be equals to 0, and the upward direction is considered to be positive. So now we have this sine component acting in the downward direction and this sine component acting in the downward direction. So we will have FAD sine of alpha. So alpha is 26.565, and FAD sine of alpha is acting in the downward direction, so this is minus. And similarly, this FAB sine of alpha, this is acting in the downward direction, so this is minus as well. So minus FAB sine of 26.565, and this is equal to 0. And if we divide this whole equation by sine of 26.565, so this will cancel out and this will cancel out, so we will be left with minus FAD minus FAB equals to 0. And we can say that minus FAD is equal to FAB, or we can say that FAB is equal to minus FAD. So one of the direction of the force is not accurate, right? So now if we apply the summation of forces along x equals to 0, towards the right is our positive x direction. Now as we can see that FAD cos of alpha, this is acting towards the left, so I will write minus FAD cos of alpha. Now alpha will remain the same, that is 26.565. Then we have this cos component, this is acting towards the right, so we will write plus FAB cos of 26.565, and then we have AX. AX is 2 divided by 3P, and it is acting towards the right, which is the positive direction. So plus 2 divided by 3P equals to 0. So now if I divide this whole equation by cos of 26.565, so we will have cos of, so this will be minus FAD plus FAB plus 2 divided by 3 cos of 26.565 P, this is equal to 0. Now we know that minus FAD is FAB, so we can replace this minus FAD with FAB. So we can write this as FAB plus these same terms. And this is equal to 0. So 2 FAB, and we can bring this term to the other side of the equation, so this will become minus. So minus 2 divided by 3 cos of 26.565 P, and if we divide both sides of the equation by 2, so we will get it like this. So FAB is minus P divided by 3 cos of 26.565. So 1 divided by 3 cos of 26.565, this is equal to minus 0.373 P. So FAB. Now we got the negative sign. The assumed direction of FAB is not accurate. FAB is acting towards this joint A. So this means that the AB member is in compression if its force is acting towards that joint A. So now we can say that FAB magnitude is 0.373 P, and this is the compressive force. And similarly from here we know that FAB is equal to minus FAD, or we can say that FAD is minus FAB. So we can say that FAD is equal to minus FAB. This is the actual value for that assumption, so that is minus. So FAD is minus FAB, that is minus 0.373 P, which is equal to plus 0.373 P. So this is FAD. And since we got the positive sign and the assumed direction of FAD is towards the joint A, so it is also compressive. So FAD is compressive force and AD member is in compression. Now next we are going to consider joint D. So at joint D, this FED is equal to 0. So there is no need to draw FED force since its value is 0. So we will have FAD, and FAD is compressive force. So it's going to act towards this joint D here. We know FED force value, and let's assume that CD member is in tension, so its force must be acting away from joint D. And similarly, let's assume that this BD member is in tension as well. So the force must be acting in the downward direction like this. So let me draw joint D here. So here we have FAD. Its value is 0.373 P. Then we have CD. This is FCD, and we have FBD. So this is FBD. Now we know the angle of FCD, the angle of this FCD, and the angle of FAB. If we know this angle alpha, so this FAD is going to make that same angle alpha here. And since we have that same triangle here as well, so we will have that same angle alpha here. So we have this same angle alpha, and we have that same angle alpha here as well. And that alpha angle is known, which is 26.565. From here, this is 26.565. So now we can resolve this FAD into its components. We will have one component in this direction, and we will have one component in this direction. So this is FAD cos of alpha, and this one is FAD sine of alpha. And similarly, FCD will have one component in this direction. This one will be FCD cos of alpha, and this one will be FCD sine of alpha. Now considering this joint D, if we apply the summation of forces along x, that must be equals to 0. Towards the right is our positive x direction. So we have this FCD cos of alpha, so plus FCD cos of alpha, and then we have FAD cos of alpha, so plus FAD cos of alpha. This is equal to 0. And if we divide the whole equation by cos of alpha, so we will get FCD plus FAD equals to 0. And from this we can say that FCD is equal to minus FAD. And similarly, if I apply the summation of forces along y equals to 0, and this is our positive y direction, now we have FAD sine of alpha, so plus FAD, and FAD magnitude is known, which is 0.373 P sine of alpha, And now the alpha angle is 26.565. So 26.565. Then we have this FCD sine of alpha. So we have minus FCD sine of alpha, which is 26.565. And now we know that FCD is equal to minus FAD. So from this we can say that FCD is equal to minus FAD, and FAD is 0.373p. So the minus sign tells us that the assumed direction of FCD is not accurate. FCD is acting towards this joint D, so this means that FCD is also compressive force. So we can say that FCD magnitude is 0.373p, and it is the compressive force. So we need to plug in this value here. So this is minus FCD, and since this equation is according to that assumption, so we have to put that minus value here. So that will be minus 0.373p, and then we have this is acting in the downward direction, and this is FBD. So this is in the downward direction, so minus FBD equals to 0, and this will become plus, so plus 0.373, and if I bring this FED to the other side of equation, and this will become twice. If we add both of these, so this will become twice. This is 0.373p. So this is, we can say that FBD is equal to 2 into 0.373p sine of 26.565. So this is 2 into 0.373 into sine of 26.565. So this gives me FBD equals to plus 0.333p, and the plus sign indicates that the assumed direction is accurate. BD member is in tension. So this is 0.33p, and BD member is in tension. So now we know FAD, we know FAD, we know FCD, and we know FBD. Now we need to find the force in this BC member. So for that we have to consider the joint B. So let's consider the joint B. So at joint B we have the BC force, and here we have AB. So AB is in compression and its value is 0.373. So if it is in compression, it must be acting towards that joint B. So this is FAB, value is 0.373p, and then we have at joint B we will have FBD, and FBD is, the BD member is in tension, so it must be acting away from joint B in the vertical direction like this. So this is FBD, its magnitude is 0.33p, and similarly at B we will have BC. So let's assume that this BC member is in tension as well. So let's say that if it is in tension, the force must be acting away from joint B. So this is FBC. So the only unknown is this FBC. So now again we need to resolve this FBC. We know the angle of FAB with the horizontal, which is alpha. So if we draw that angle here, so both of these angles are alternate angles, so we will have that same angle alpha here, and we will have that same angle alpha here as well. Since this is d divided by 2 and this is d, so we will get that same angle alpha. So here we have angle alpha, and here we have that angle alpha, and similarly we can resolve FBC. So it will have one component, that is FBC cos of alpha, and this will be the sine component, And similarly, this FAB will have one component in this direction and it will have one component in this direction. So now if we apply the summation of forces along Y while considering joint B, the summation of forces along Y, that must be equals to 0. And this is our positive Y direction. So now we have FBD, that is plus 0.333p. Then we have this component of FAB, it is acting downward, that is minus 0.373p. And this is the sine component, the sine of alpha, and alpha is 26.565. And similarly we have this sine component of FBC, so which is plus FBC sine of alpha 26.565 equals to 0. So now if I divide this whole equation by sine of that angle, that is sine of 26.565, this will cancel out, so we will have this FBC here, and this will cancel out as well. We will be left with 0.373p. And now from both of these terms we can take this p as common, so we can write it like this. So this is 0.333 divided by sine of 26.565 minus 0.373. So this gives me 0.372p approximately, plus FBC equals to 0, and FBC is equal to minus 0.372. This is 372. And the negative sign tells us that the FBC is acting towards this joint B. So this means that the BC member is in compression. So FBC is 0.372 P, and this is also in compression. So we have determined the forces in each and every member of this truss in terms of P. So this is the solution of this particular problem. I hope this will help you in your learning. Let me know in the comments if this helps in your learning. Do hit that subscribe button if you haven't done it yet.